go ahead and get started. It's my pleasure to introduce Professor Harry Collins, who's a social scientist at Cardiff University. He's also a fellow of the British Academy. And today we'll be talking about some considerations arising out of the search for and detection of gravitational waves. Thanks, Professor Collins. He also said he's happy to take any questions during the talk if you'd like to interrupt and do so.
Okay, as I said, thanks for inviting me. I'll give you some sense of the talk. The first thing I've got is 30 slides, of which represent a condensed timeline of gravitational waves and my involvement in it. I'll go through these very, very quickly. Then there's one slide, quite a complicated one, which talks about some spin-offs from this study that I did, which lasted a total of about 45 years. Then I'm going to get to the crunch, which I want to make. I want to say that the way scientists present their results ought to change. And then, if we still have any time, I'll go in for a little counterfactual adventure, explaining that without Joe Weber, we still wouldn't have. Joe Weber, who was the person who thought he had discovered gravitational waves in the late 60s and early 70s, but was agreed to be wrong. Not that he agreed he was wrong, but everybody else agreed he was wrong by about 1975. But I'm going to argue that without him, we still would not have seen gravitational waves, nor, since I meant to mention black holes, would we know about intermediate mass black holes, which I think have been only known about since the detection of gravitational waves. So I'm going to be going fast, but don't hesitate to interrupt if you want to ask a question. So in 1916, Einstein theorized the existence of gravitational waves, but says they're and continued to say that they're too weak to be of interest to experimental physics. Anyway, he changed his mind about their existence at various times after that. In the next 50 years, theorists are arguing about whether they existed and whether they were in principle detectable, agreeing that they were too weak to detect in practice. But things got interesting in the 1960s. Joe Weber, an engineer physicist at the University of Maryland, built a resonant bar apparatus to detect them and claimed positive results towards the end of the 60s and early 70s. And the high point of his discovery claims was the early 1970s. And that's when I started my field work, which looked like this. There I am in 1972 in a Ford Galaxy, which cost $250, with the wife of one of my friends in Philadelphia, before setting out across America to interview scientists, mostly on Route 66, actually, which is rather nice. And I was looking at four fields of physics, actually: T-lasers, not physics, paranormal phenomena is not physics, the theory of amorphous semiconductors, which I never managed to understand, and the detection and arguments over the existence of gravitational waves. This is Joe Weber, who built the thing. He first came to light in 1959. He won something called the Gravity Research Foundation Essay Prize, and he wrote a book in 1961 called General Relativity and Gravitational Wave Physics. This is a diagram from it, and it's his basic diagram of how to detect gravitational waves. You see on the left the piezoelectric crystals. They were actually eventually linked to huge bars of aluminium alloy, and then he compared the signals that he got from two separated ones. There's Joe Weber working on his bars of aluminium alloy with piezoelectric crystals glued to their surface. They would produce electrical output when the bars resonated. That's a schematic diagram of what the whole thing looked like. Of course, the resonant bars had to be isolated from terrestrial noise. So they were put in a vacuum chamber. And quite important is the acoustic isolation, which is shown there as a layer of rubber and lead, which worked quite well actually. And then he had lots of instruments to look for ambient noise so he could subtract it. This is the sort of output, what his output from his resonant bar detector looked like. And crucially, he mounted two separated by 1,000 miles, one in the University of Maryland, his home one, and one in Argonne near Chicago. And then somewhere along the line, and sorry, I should just say that this is the way it's still done to this day. Two separate detectors, at least two separate detectors. And then you look for coincident signals between the two distant detectors. And then Joe Weber invented, or came up with anyway, after talking to people, his idea of delay histogram, which is still used. And what you do is you take the output from one of those detectors and you delay it by various amounts. Whoops. And what counts as a signal is when at zero delay, you have more energy coming into the bar than you have when the signal from the bar is offset. That's what counted for Joe Weber. And it's still essentially what's done today. So most of what's done, not the actual apparatus, but most of the principle of detecting gravitational waves, this delicate signal, was invented by Joe Weber. Anyway, he was largely discredited by 1975. And then what happened then was that more sensitive cryogenic bars were built. These were cooled down to near absolute zero. And later we had a war between the bars and the much more expensive technology which came along afterwards, the much more expensive technology of interferometers. Joe Weber could build a bar for maybe $100,000. The interferometers were costing hundreds of millions. My first book which involved this was written in 1985, and a second edition in 1992. But I'd written papers beforehand. Then we had the period of people trying to replicate Joe Weber's results. This is one of Joe Weber's assistants saying that he's willing to give everybody all the information they asked for in order to try and replicate Joe Weber's results. There's one of the cryogenic bars, this one in Frascati in Italy, with Eugenio Coccia standing in front of it. And this was cooled down. This was described to me as the coldest large object in the universe, which I thought was sort of tickled me. This is similar thing in Louisiana, opened up so you can see the bar at the bottom there. This is David Blair in the middle, who built one in Perth, Australia. Guy on the right is Guido Pizzella, who is associated with the Frascati detector. He claimed to have seen gravitational waves from a supernova. Anyway, discredited. The more sensitive cryogenic bars make more disputed claims. Develops, as I said, between a war between the bar and the interferometers. None of the bar claims, there were about half a dozen of them, survived. LIGO, the Laser Interferometer Gravitational Wave Observatory, was funded and starts building in 1994. 2002 to 2010, the first detection runs of initial LIGO. Nothing was seen, and I wrote my book, Gravity's Shadow, in 2004. That's an interferometer. Those are some prototype interferometers. There's a team at MIT and a team at Caltech who eventually were forced to combine by the National Science Foundation to go in for one large project. The large project was initially run by these three, known as the Troika. That's Ray Weiss from MIT on the left, that's Kip Thorne from Caltech in the middle, and that's Ron Drever, who was recruited from Glasgow on the right. the two on the left eventually won Nobel Prizes. Ron Drever died before the dispute could really get going about whether he should get one or not. There's an additional person there. You see Kip Thorne, Ron Drever, and Robbie Vogt, who was the first director of LIGO when LIGO started to become a big science project and put it on track to become a big science project. And there's Barry Barish and Gary Sanders, who actually completed the process of turning it into a big science project. Part of that process was a big bunch of interferometer scientists at Caltech leaving, resigning from the whole project. Those are the two initial full-scale interferometers. The one on the left is in Hanford Nuclear Reservation. The one on the right is in Louisiana and a kind of swampland. I remember what was my involvement? I went to nearly all, from about the late 90s on, 1990s onwards, I went to all their meetings of this team, got to know them all very, very well. I remember before these started building, I sat down with Barry Barish and had a long argument with him, telling him he didn't know enough about interferometry to justify building these hugely expensive interferometers. He said he did. I thought I won the argument, but he went ahead anyway. And of course, he turned out to be right, which is just as well. Then what do we got here? What happens after this is that in 2014, nothing had been seen by initial LIGO in the way of a gravitational wave. In 2014, advanced LIGO neared completion. This was a much more sensitive version of the same device built in the same housings. And then on the 14th of September 2015, a putative signal was detected. I remember sitting in this same room as I'm sitting in now, reading an email that evening, September the 14th, saying we found an interesting signal. I didn't take any notice of it. LIGO was always finding signals, which turned out to be noise. But remarkably, this one, within about 3 days, people had decided this was something real that had to be really followed up. And it turned out to be the first detection. They spent 5 months checking all imaginable problems and at the same time denying rumors, because they decided they wanted to keep their project secret until they had checked out that this really was the first discovery of a gravitational wave. After the 5 months, eventually it was publicly announced that they had discovered a gravitational wave at major conferences, including the American Physical Society. There was a publication followed, and it was followed by Nobel Prizes. And I wrote my book, Gravity's Kiss, which will show up a bit later, in 2017. The event, this is how I describe it in the book, 1.5 billion years ago, and 1.5 billion light years away, two black holes, 36 and 29 solar masses respectively, collided, losing 3 suns worth of mass, which was converted into energy, compared to about 1 gram for the first atomic bomb converted into energy. How do we know they were 36 and 29 solar masses? We didn't know for a while, but the team had built a template bank of models of collisions of black holes and black holes with neutron stars and neutron stars and neutron stars. And the signals from this event fitted the model, which had 36 and 29 solar masses. The effect on the 4-kilometer arms was a relative change of length, detectable down to 1/10,000th of the diameter of a proton. So you've got to find that change. I've got to see it. The arms wiggling around to the tune of 1/10,000th of the diameter of proton, and the arms are 4 kilometer long. So as you can see, the whole project is completely mad. The discovery conference announcement was on February the 11th, 2016. I remember the then director said, "We have detected gravitational waves. We did it." The paper title was Observation of Gravitational Waves in the Binary Black Hole Merger. And it sent shivers down people's spines that this had finally happened after 100 years since Einstein suggested that they existed. There's some of the local conferences. I was at that one, which is second on the right down, which was in London. The one in Washington is opposite it on the left, but they're all over the place. That one down on the bottom right is in CERN. Yeah. These are some newspaper front pages at the time. This is a song that somebody made up for the American Physical Society conference to the tune of "I'm a Believer. I thought waves of gravity waves were fairy tales, fine for dilettantes, but not for me," and so on. And that is my book, Gravity's Kiss, which was published in 2017. And I stopped working in the area round about 2018 or a bit later. I didn't like the feel of the gravitational wave field very much any longer. I think I'd been very, very lucky with choosing this as a long-term project. For the whole time I was with the gravitational wave project, the gravitational wave physicists were themselves outsiders. There was huge opposition to the project, quite reasonable opposition in my view. It seemed an impossible thing to do, to detect these incredibly weak gravitational waves. So weak when they hit the Earth, they were strong when they left the black holes.
I have a question.
Was that a question?
Yeah, I have a question. Yeah.
Sure.
You hear me?
Yeah, you speak very loudly, please, because it's difficult to
very
hear.
loudly. Okay.
Oh, sorry. I can unmute you.
Oh, then let me mute here.
I can speak now?
Yeah.
But is Harry hearing what I'm saying?
Yeah, I can hear just about.
Oh, I think, okay. Yep, mute.
Unmuted by also.
Yeah, I'll switch both on.
Have you asked the question?
Yeah.
I can't hear anything.
I think we should leave it on my mic. Okay.
Okay.
Okay?
Yeah.
Yeah, so, you were talking about the whole question whether they will detect waves at all. And it's an
Yes.
engineering challenge and all of that. But earlier, as you mentioned, there was also the question of whether these waves are real at all. Are they a real physical effect? And as you said, for decades, people were arguing.
Yes.
Was that all settled before Weber and then later LIGO started doing their work, or was that discussion still ongoing?
That's a very good question. And I'll give you my view on it. That no, I don't think it was settled before Joe Weber started work on it. My own view is that by actually building a detector, Joe Weber shut everybody up and stopped the objectors. It wasn't a piece of physics. It was a piece of creating reality. By building a detector, even though this detector never did detect gravitational waves, but by building a detector, I think Joe Weber changed people's minds and convinced them that that gravitational waves could be detected on the surface of the Earth and could be detected in principle. One has to add something to this, because gravitational waves there's also a claim had been made, which had never been denied, that the existence of gravitational waves had been shown by work done by astronomers Hulse and Taylor and Weisberg, who'd observed a binary star system in which one of the components of the binary system was a pulsar. And because it was a pulsar, it could be used to time the very slow degradation of the orbit of the binary system. This is not an in-spiral. It was the slow degradation of the orbit whilst it was still orbiting properly. And over a period of years, they discovered that the degradation of the orbit was exactly consistent with the loss of energy that there should have been according to the gravitational wave emissions of a system such as this. A bit later in the talk, if we get to it, I'll show you the graph that they produced to demonstrate this. Is that okay?
Thank you.
Okay.
Could I ask a follow-up? So what do you think the conclusion would have been if LIGO had continued to be unsuccessful?
Just say that again, Helen.
What do you think the conclusion would have been if LIGO had just continued to not be successful in any detections?
Well, I think by the time LIGO had built advanced LIGO, I don't think it would have been too disastrous. I mean, strangely enough, this was a question that a journalist asked me. They telephoned me and asked me when advanced LIGO was coming on air, and said, what's going to happen if advanced LIGO doesn't see any gravitational waves? And quite honestly, I didn't expect it to see any gravitational waves. And I'm not sure if anybody else did. You know, most of the scientists, they weren't sure that it was going to see any gravitational waves. I mean, been looking for years and years and nothing had shown up. But what I replied to the journalist was that, well, it won't be a disaster, because the only thing that needs to be wrong for LIGO not to have seen any gravitational waves yet is for astrophysical notions of what's in the heavens to be wrong. There just could be no suitable emitters around. So what I think would have happened is that they'd have tried to go on and build another generation of still more sensitive detectors, which of course they have done subsequently. Whether that next generation would have been funded, I don't know. If I had to guess retrospectively, I'd say it probably wouldn't have been funded, because a much better bet is to try to detect gravitational waves with a LISA, which is a satellite system shot into space. And I can explain why that's a better bet later, if you like. But that's my guess. It wouldn't have been a disaster for physical theory. Einstein didn't have to be wrong. It just had to be the astrophysicists who were wrong in predicting that the heavens were populated by certain sort of systems that they weren't. And indeed, the astrophysicists were wrong, because what everybody spent their time looking for with gravitational wave detectors was in-spiraling binary neutron stars. And that's one of those still hasn't been seen. At best, 2 systems have been seen where one of the components is a neutron star. So what was seen, which was in-spiraling binary black hole, and since subsequently 100 or so more of them, it wasn't known if such things existed until the first detection. Okay,
Thank you.
all right, I'll carry on. Where did we get to? So yeah, I said I stopped because gravitational waves has become a branch of astronomy. They're now detecting inspiraling binary black holes routinely, and the scientists have become famous, and famous scientists are much harder to deal with than people who are the butt of everybody's disdain, which they were for about 45 years. So as a sociologist, I'm the butt of everybody's disdain. So we got on pretty well, and I really enjoyed it. It was a wonderful period of my life and a wonderful project. So what were some spin-offs? Now some spin-offs for me as a sociologist, because I was not thinking of myself during this time as a historian of science, though I think if you read it,
We have a hand raised if you don't mind
sure.
taking it. Vitaly, go ahead.
Hello, can you hear me?
Yes.
Sorry, I cannot turn on the camera here. But so my question is the following. You have worked for many years with the gravitational wave collaborations.
Yes.
And you observe how they work, what they discuss, and how they come to the conclusions. What is your impression? Is it actually required to have any kind of advanced physics education to discover such thing like a gravitational wave, or like something like interactional expertise is sufficient for somebody with say high school background in physics? Thank you.
No, I mean, there's no way that gravitational waves could have been discovered without the mathematics. I mean, for example, as I said earlier, a template bank was built of models of various inspiraling binary systems, and that was a matter of mathematical analysis, computer modeling. Took many years. And of course, Einstein developing his theory was highly mathematical. The question now, whether anybody can do it with sort of high school physics like me, there's a division of labor in physics. This is the conclusion I reached watching this. You have to have brilliant mathematicians or very good mathematicians in a collaboration like this, but not everybody has to be a very good mathematician. For instance, Ron Drever, the person who who died before he could be considered for the Nobel Prize or given the Nobel Prize, was not a great mathematician. People told me that from the outset. At first I thought, oh, they just mean he's not a genius. But eventually I discovered I got to know Ron Drever very well. When they said Ron Drever wasn't a very good mathematician, they meant, he's not. It turned out that he's not that great, not that much of a better mathematician than me, but he had a terrific physical insight into how the world held together. I think if I had been clever enough to be a physicist, and if I'd been a physicist, I would have been a Ron Drever-like physicist, because I was never a great mathematician. I can do some calculus and so forth, and I have done. I've written computer programs, but I'm not. The reason I couldn't understand the theory of amorphous semiconductors, which was one of my fields, is that my mathematics wasn't good enough. So the answer is you can contribute to gravitational wave physics without being a great mathematician, but the collective field of gravitational wave physics wouldn't exist without it being heavily populated with very good mathematicians indeed. As for interactional expertise, to have good interactional expertise is a high bar. I spent 5-10 years having enough interactional expertise to pass as a gravitational wave physicist in an imitation game. But part of the rules of the questions I was asked there was no mathematics. But there were questions like, given a gravitational wave form of this type, would an interferometer be able to see it? And actually, I answered that question better than the physicists, because I could sort of see the shape of the thing. And also bear in mind that somebody like Gary Sanders, who was the project manager of LIGO and therefore made huge contributions to it, he agreed with me that what he had was mainly interactional expertise. And if you send me an email, I'll send you a paper I wrote with Gary Sanders where we discuss interactional expertise at the point when he had become the director of the 30-meter telescope project. He says that the physicists could see that his interactional expertise was good enough to direct the project. And so don't knock interactional expertise. One of the things that worries me is that people tend to use the idea of interactional expertise that says, oh, you only got to talk to a few people and you become as expert as them. You don't. It takes a long time if you're going to be able to pass as one of them. Is that okay?
Thank you very much. Very interesting.
Yeah. Okay, so where are we? So some spin-offs for me as a sociologist. Well, if you know some sociology, you'll have heard of the sociology of science. You'll have heard of the experimenters regress. That was the first spin-off. Then I learned a lot about the difference between big science and small science. And I learned why Ron Drever had to be sacked from the project and why its first director, Robbie Vogt, had to be let go from the project, because neither of them could go all the way to big science. The crucial thing about big science is you have to not go for the very best solutions to things, but you have to be ready to make compromises. And Drever couldn't make the compromises. He could only continually go for the frontiers of the best. And Vogt wanted to work in a small team, a small closed system team like Lockheed Aircraft. That was one of his analogies. And to do big science, you've got to open the boundaries up to a much wider group of people, which Barry Barish and Gary Sanders, who took it over, were ready to do. I learned an awful lot about statistics, including the role of the trials factor, otherwise known as the look elsewhere effect by physicists, which most people who do statistics in the social sciences and so on don't understand anything about at all. And therefore I was, the fact that we have this so-called replication crisis in the social sciences, in psychology and medicine is no surprise at all, because these are sciences. What happened there? Sorry. These are sciences that use a 2 sigma standard for publication. Physics, like gravitational waves physics, uses a 5 sigma standard, and the difference is there for a very good reason, that the physicists actually do enough experiments to discover what level of statistical significance you need if you're going to be able to rely on your results. And 2 sigma is not really much better than about 50-50, even though it says it's 1 in 20. This is because of systematic errors and things like the trials factor. So I learned a lot about statistics. Then the difference between interactional and contributory expertise came out of this exercise, and I learned how the division of labor works. Division of labor works with interactional expertise, because where you have a division of labor, people are contributory experts and they can only do one practical thing. So they have to have interactional expertise to learn how to make their practical skills interact with each other. What came out of this was the imitation game, which is a Turing test but played with humans. I managed to pass as a gravitational wave physicist in one of these imitation games. I did rather well, 2 of them. I did rather well. Then one of the things I showed was a sort of Duhem-Quine effect. The claim to have discovered gravitational waves could only be made on the basis of various assumptions, especially over the social integrity of the team. You know, that wasn't physics. If you're going to be sure that nobody's hacked into the instrument and put a false signal in, pretending it to be a real signal, you've got to be able to trust your colleagues. And that's a social judgment, not a physical judgment. And then most important of all, one of the things I concluded was that science's integrity, one of the things I concluded and one of the things I'm writing about these days is that science integrity is more important than science's findings. And that's what I'm going to go on to talk about now. That's the complicated single slide of the spin-offs. And now let's get on to science, truth, and Trump. They did, after the initial discovery, 5 months of testing and 5 months of deceiving. Can you see that? And deception just behind where it says you're screen sharing. The community determined that the signal and the verification process should be hidden until that they were sure they were right and they were ready to announce it in public. And there was a kind of warning, because if you heard of Bicep 2, that was the false claim of having discovered primordial gravitational waves, which turned out to be wrong. And the team were determined not to make that kind of mistake. But they wouldn't, you know, the Bicep 2 didn't have to be there. They were determined not to make the mistake anyway. But they wanted to keep everything secret until they were ready to announce it. It was difficult, though. Rumors began almost immediately and grew in volume and accuracy. You know, people were saying, where are all the gravitational wave physicists gone? Why are they spending all this time in meetings? You know, they were doing the equivalent of military generals when they look at the ground and see that there are vehicle movements going towards unusual number of vehicle movements going towards headquarters. They knew there was something going on. It was understood within the community, however, that the work should be kept secret and journalists should be misled or even misinformed. Then in early January, can't get rid of that, can I? Anyway, in early January 2016, yes, a careful reading of the rumors would tell you nearly everything you need to know. It had been said that 2 events had been seen, and there was a second event, the so-called Boxing Day event, which happened on Boxing Day, and that at least one of them was a binary black hole. And it has been said that the event had occurred during the engineering run before the observational run had begun, so it could not have been a blind injection. Lawrence Krauss was saying this kind of thing. Sorry, I haven't got time to go into it in detail, but we can go into it in detail in the question session. And this came out from headquarters. This kind of pressure is very damaging to activities, especially at the time when we are trying to get not just the detection paper results reviewed, but when our attention should be focused on the results we want to present. Please refrain from talking to any non-LVC member, that's LIGO or Virgo collaboration member, about preliminary results. We need not only our internal review, but peer review before sharing results, and we don't have either yet. 2 things happened on January the 11th. A new tranche of rumors came to my attention as a result of a phone call from a Nature reporter whom I spoke to around September 26th. He has heard some new rumors, and what's my opinion of them? These rumors are pretty startling, including one that the signal happened during the engineering run before the blind injection program had begun, so it could not be a blind injection. One of the stories that the scientists were telling to journalists was, we don't know whether it's true or whether it's a blind injection. That's a test injection that the managers put in to test the readiness of the team to see a gravitational wave if it's there. 2 previous blind injections had been done in initial LIGO. And I wrote a book about each of them. And you could say, you know, it might be a blind injection. And some people said that, even though they knew they were lying. I say to the reporter, I have not heard those rumors. That is literally true. I have not heard the rumors, so I'm not lying. But I am certainly engaging in deceit, and I wish I did not have to. This phone call lasts around half an hour, and I'm essentially engaged in deceit for half an hour. This isn't right, and I feel terrible. So I'm in my duty. I'm cross-cutting duties. One was to tell the truth to journalists, and one was not to let down my colleagues in the gravitational wave business. And, you know, the second was more important, but it made me feel pretty bad. By now, the end of January 2016, more than 1,000 scientists are lying, misleading, and paltering to keep the discovery secret. What is happening, as I've already suggested, is that as this episode reaches its denouement, a generation of scientists is being trained in the arts of deception. That is exactly the opposite of what science should be doing. It should be leading democratic societies in a demonstration of integrity. And in my book, I set out a table, in my book, Gravity's Kiss, I set out a table saying how I think this discovery should have been announced. That they should have made a pronouncement right at the beginning saying, you know, we found something interesting, but of course we don't yet know it's a gravitational wave. And then, because we've got to do a lot of testing, and then you go through a series of stages. The first thing you'd say is there's enough going on here to make us busier than usual. And if it turned out that it's a false alarm, you'd say, but it was a false alarm. Second stage, you'd say, we're analysing data that might or not lead to interesting directions. And if it didn't lead anywhere, you'd say it didn't lead anywhere. And you might say, we're clearing diaries in case we need to make an announcement. And then you say, if it doesn't go anywhere, unfortunately, we discovered a mistake. And then you say, a paper has been submitted and is being refereed. And if it's rejected, you say the paper is being revised or it's been rejected. And then you say, we'll make an announcement on a certain date unless things go wrong. And if things go wrong, further scrutiny shows the result is not reliable. But watch this space. And so that's then, if all goes well, you do the unveiling, which was done. And if it doesn't, you say, oh, look, we've got to delay further. It turns out to be a disappointment. And what I'm saying is that you don't need to keep everything secret for these 5 months so that you can withdraw the discovery like a rabbit from the magician's hat. It's actually much healthier if you show to the public the incredible difficulty of confirming a discovery and go through it step by step so that the public really knows what science is. And I wrote this up. I discussed it with a gravitational wave physicist, and I didn't manage to convince anybody. Well, maybe one or two of the younger ones agreed that this was probably right, but the senior physicists either didn't understand what I was trying to say. I mean, quite a few of them didn't. They told me, don't you think we should have done this 5 minutes of testing? And these are people who'd heard rumors that that's what I'd said, though I'd never said it at all. But physicists don't know that they're supposed, you know, if they're going to accuse you of something, they don't know that they should read your work first. That's okay. That's the culture of physics. If they've heard it from somebody else, they go with that. And this is why my claim is that the most important product of gravitational wave physics is not gravitational waves, it's truth. And I wrote that in the book. And I think that this claim is becoming clearer and clearer as we reach further into populism and the erosion of truth under populists who are moving towards fascism. And as I said, that's what I'm writing about now. So there's one more section of this talk, that's the counterfactual business about Joe Webber and why I think that gravitational waves wouldn't have been discovered to this date if it wasn't for Joe Webber. But I'm going to pause there to see if there are questions about what I've said so far. and then I can finish off with that if we still have time.
Ramesh, go ahead.
Yeah, so I do have a question on this very interesting suggestion of how it should be done. I'm all for this. I mean, it sounds like a great
Louder,
idea.
please, louder, louder.
This sounds like a great idea, but I'm confused about the details. So in these intermediate stages, do you just say what's on the left, or do you show the data and say, look, this is what we see. It's not yet phi sigma. We still have to check this, systematic effects, etc. Because if you do that, somebody else is going to take your data and probably run with it. So how do you draw the line? And is your reporter going to leave you alone if you make a statement and don't show the data?
Yeah, I don't know the answer to that. And I think the answer to that should be given by physicists, not by me, because I don't know the extent to which people might be able to preempt you if you'd given out some of the data. But I think this would still work even if you didn't provide the actual data. You just say, we're looking and we're testing and we're checking everything, but we haven't got there yet. But I'd rather, what would make me perfectly happy is that people accepted the principle of this table and then argued about it among the physics community about exactly how this should be executed. I'm not claiming that this is the perfect execution of the idea. Okay, any more questions?
Yeah. So with the Event Horizon Telescope, we had a similar long period of about 9 months between seeing the first images and being ready to show them to the world. And one of the factors that entered into it was the degree of centralization or dispersion among the different labs around the different countries, and who would announce. So we ended up having 6 or 7 different announcements all over the world, timed to the second as to when the picture could go up on a screen, because one of the issues was not just vis-a-vis competition vis-a-vis other groups that could have processed the data. It was trying to avoid any one group claiming, being represented in the press as having made the discovery. So there was a great coordinative effort, and part of the sense that there's the centralized control was to give everybody a sense that all the groups were being fairly and equitably represented in having participated in the discovery. Was that any kind of centralization question important in LIGO, or was it sort of obvious that everybody was working under a centralized leadership?
Yeah, that's an interesting question. No, there was no problem of this sort in LIGO. On the contrary, the first discovery was definitely made by the 2 American LIGO detectors, the one in Hanford and the one in Louisiana. But everybody worked hard under Barry Barish's leadership to make sure that Virgo, the French-Italian detector, and the Glasgow detector cited in Germany, Glasgow Scottish German detector, were also given credit as part of the team. So it was almost the opposite of what you were saying. The credit, there was more credit given to people who didn't contribute much than one might have expected in a highly competitive circumstances. Now, if I can go back to the earlier question, I think there's a real danger about having other people steal your preliminary data and work it up into a discovery, because I sincerely believe that the only people who are capable of doing it properly are the original team. You've got to know the apparatus inside out to make sure, certainly in this case of gravitational waves, to make sure you're doing the calculation right. And in fact, there was a team from the Niels Bohr Institute in Copenhagen who came up after the initial discovery announcement and saying it was false. And they'd done their calculations on the data that had come out and shown it was false. And this would have been a great little story for me to write up. But in the end, I didn't bother to write it up because I could see that they just didn't understand the data. And this is one of the problems of the modern movement towards open science, that you're inviting all sorts of people in to comment on your scientific work who don't have the depth of expertise and skill that you need. You've got to have worked on that apparatus. I mean, I could prove this to you more, but I don't want to speak too long about this. Peter, I think it was Peter, wasn't it, who asked the second question about this. That kind of competition among scientists, I do not find endearing. I wish scientists were not competitive. In fact, years and years and years and years ago, I wrote a paper about science policy saying the money should always go to the people who, or more money should go to people who didn't discover it first, because they won't be famous. They'll be cheaper scientists. Their salaries will be lower, but they'll still be discovering the same science. And who cares who makes the first discovery? Why should we care? You know, part of the problem, as you probably realize, is if you're writing about stuff like this, people are extremely jealous of how much mention they get in say, my books. And I feel slightly edgy about it, and I'm very careful about it. But there's at least one person who felt that they didn't get enough credit in the book I wrote about the discovery, and was very nasty about it indeed. But you know, science is publicly funded, and the public has no reason to care about which individuals make the first discovery. I don't think it's important to science. What's important to science are the discoveries and correct moral integrity, telling the truth. So I wouldn't count what you're saying about everybody making sure they get a fair crack of the whip as a reasonable objection to my suggestion in that table.
Yulish has his hand up on the Zoom. Go ahead, Yulish.
Hi. Yeah, it's a clarification question about something you said earlier in the talk. So I'm curious about this moment where sort of I think you put it as astrophysicists were wrong because of the kind of like expectation that the majority of events will be provided by the neutron star mergers. And I'm just curious if kind of there was like an expected rate that the astrophysics community was sort of like expecting. Sorry, the estimated, was there an estimate of the frequency of those events? And if so, was it kind of like explicit and widely shared among the community, or was it sort of?
No, I think what I said was slightly misleading there. What the reason that everybody was looking for neutron stars, or something with neutron stars in it, was because that's the only thing that had been seen in spiraling. You see, the Hulse-Taylor thing was one of those, although it was early in its life, so it wasn't getting anywhere near in spiraling. So everybody was expecting to see neutron stars, but there wasn't any rate. No. And it's just that those one or two that had been seen by astronomers formed the expectation. The basis of all the calculations of the range of the interferometric detectors was based on neutron star in spirals. And so everybody was thinking about neutron star in spirals. They weren't thinking about black hole in spirals. I mean, Kip Thorne had suggested that the first discovery might be a black hole in spiral, but Kip Thorne had a huge range of things that might be the first discovery. And, you know, not everybody was sure, given the energy in a pair of, in a binary black hole system, whether the universe was old enough for enough energy to have decayed for them to be in spiraling. And it turns out that, you know, the ones that have been discovered are all fairly small. You know, a few tens of sun masses. So if I'd made it seem that people had a clear idea of the existence of the rate of neutron star in spirals in the heavens, that was misleading. What I mean is that was what everybody was looking for. And one would have said, that's what everybody was looking for. But it looks like the astrophysicists' expectations formed by the fact that some inspiraling neutron star systems have been seen were wrong.
Cool. Thank you so much.
Any other short questions? We're just about out of time. Oh, yes, Peter Lee, go ahead.
Oh, thank you very much. Short but kind of provocative questions. I like very much your suggestion about allowing scientists to publish and present and distribute information about their discoveries, like without any constraints or political limitations or whatever inside collaborations. I heard such suggestions since, I think, superconducting super collider. I think some people suggested it, but never been successful. So scientific community is very reluctant to allow multiple interpretations and multiple communications about discoveries. They like the secrecy. I think it looks like in sociology, you know, the concept of prestige. Yes, prestige is a very important concept, and many scientists, most of scientists, are concerned about the prestige, and the highest prestige goes to the Nobel Prize, of course. But unfortunately, the Nobel Prize can be awarded only to 3 people, not more than that. At the same time, discoveries are made by thousands. Would it be, I think, from your point of view, would it be a solution if such highest prestige prizes like Nobel Prize were sort of at least modified to allow to award them to many people, to multiple people, to avoid this competition and these conflicts about the priority role? Thank you.
Well, as I'm trying to say to Peter, I'm not really interested in competition between scientists for prestige. I'm interested in science as an example of decision-making with integrity. And prestige, a search for prestige, only damages that. I'd rather see scientists acting modestly and presenting to the public the difficulty of making a confirmed discovery. And this would be done not by keeping secrets and telling lies to journalists, but by, and not by announcing necessarily very much, just saying, look, instead of denying the rumors, you say, yes, the rumors are true. We are looking at something. And this is where it's got to. But it's going to take us another 5 months to be ready to announce it. Why can't you just say that? This has got nothing to do with prestige or competition. And when, after the discovery, the gravitational wave physicists got together with astronomers because they were trying to do what's called multi-messenger astronomy. I mean, you can't see an electromagnetic correlate with an inspiraling binary black hole. But if one of the elements of the binary system was a neutron star, you would see an electronic signal. And so the astronomers joined in the group in order to look for these things. And suddenly we had huge amounts of competition and prima donnaship delivered by the astronomers. And I didn't like it at all. It's one of the reasons I didn't continue with looking in this domain.
Thank you.
What time are we due to finish, Helen?
We are actually just out of time, so
Okay.
we
So I
should.
can't do my
Very true.
Joe
Yeah.
Weber
Talk and
counterfactual.
Good discussion.
Thank you so much.